Right. Thank you for organizing the seminar, and thank you everyone for coming, despite it like being so close to summer. All right. So today I'll talk about my recent work in interpreting anterior graphs from a causal perspective, and which an application which I think is quite neat that comes from this work, right? Which is constraint confounder selection, which I'll talk about if I have time at the end. All right. Cool. All right. So I'm just gonna give a quick intro to causal inference to those who are not quite that familiar with it. So essentially, in causal inference, we always assume like some sort of graphical structure, some causal structure between variables that you're interested in. For example, here we have x, and y. For example, you can think of S as a confounder, X as a treatment, and Y as an outcome. Right? So that's the standard setup. And from this graphical representation, we want to typically, like the end goal is to estimate some sort of potential outcome, which I denote here by yx, y sub x, which means that the value, the random variable y, if x had been intervened to a fixed value small x, all right? And what's important here is that this potential outcome is not the same as a conditional variable, right? It's not the same as just taking the condition of x, right? Because yeah, for example, right, in this case, yx is not the same as y, but here this one is the same as y. Sorry, the other way around. Sorry, in this case, you have yx being the same as y, but this one is not the same as y, right? But the main takeaway is that it's not these two quantities are not the same, right? That's why we need like different methodologies to tackle that. That's where causal inference comes in. All right, so how do we actually estimate this? Well, you can just do the intervention, right? That's going to be true by definition, but they're often infeasible because, for example, you can't intervene on something like an age of a patient, right? So you can't do that. So the typical approach is that we estimate this yx from observed data, right? But of course, yx, as Vanessa mentioned last week, is that it's sort of like a missing data problem, right? You don't observe these interventions. So how can you actually estimate these? You need causal assumptions. And so, for example, you have here this causal assumption where this sign here means conditional independence, which is known as conditional exchangeability in literature. All right. So, okay, so we mentioned causal inference, at least an intro to it. So like, how does the graph come in to the causal inference workflow? All right. So a graph, it allows us to encode these sort of causal assumptions quite nicely. Okay. And what do I mean by that? Okay, well, for example, here we have our causal graph structure from before. Okay. We can use this to manipulate causal assumptions to get this conditional exchangeability, this assumption out of it. How? Well, you do this graphical operation and read off from the resulting graph via Markov property on DAGs, the separation, to get the causal assumption. And to those of you in the audience who knows this node splitting operation where you split the node X into two parts that goes in and goes out, that's a SWIG operation, single wall intervention graph from Richardson, right? All right, so yeah, so that's a neat way of what you can do with graphical causal inference. All right, so to recap, what I've done here is basically I take a causal graph, in this case a DAG, I do some graphical magic on it, in that case a swig operation, and I get causal assumptions out of it, right? But a graph is just a picture, right? What the hell am I doing actually, right? Like it's just some picture manipulation, right? So what I'm actually doing is that I'm actually manipulating the causal model, right? In this case, an SCM, in the case of DAGs, that we represent using a graph. Okay, so we are essentially using a graph as a proxy to get causal assumptions out of our causal model, right? Okay. All right, so here in this talk, I'm going to focus on, given a graph, how can you go the other way back? Because here we represent a causal model using a graph. So here I'm going to say that given a graph, what causal model is suitable for that graph, all right? And okay, so why am I interested in this problem? Well, as we will see, okay, the causal graph here, for example, the one I showed you guys previously with the graphical operation, that's a DAG. It doesn't have to be, right? So for example, when it's a DAG, I'm just going to start with the basic first. When it's a DAG, the quite widely used interpretation of it is that we can think of it as an SCM, a structural causal model here, all right? Where you have independent noise terms, epsilon 1, 2, 3 for each that you assign to each node. Then you have functions which maps the value of the parents and the noise of the node itself. For example, here you have 3 taking in 1, 2, the parents, and the noise of 3. Okay, right? So that's the interpretation. Okay, now here we say something else. We say that, okay, in this case, in the case of bidirected arrows, okay, what does it represent? This is an ancestral graph, by the way, right? Okay, so in this graph, it's basically an extension of an SCM, structural causal model, except now we allow for the noises, epsilons, to be potentially dependent when there is a noise, when there exists an arrow in between them, a bidirected arrow between them, right? Double-headed arrow between them. Okay, and this is the interpretation from Richardson and Spertes. All right. Okay, so but that's not all. We can go one step further. We can also include undirected edges lines here. Okay, so how do you interpret this? Well, according to Lauritsen and Richardson, we can think of it as like a chain component-wise SCM, where a chain component in the graph just means that a set of nodes that are connected via a sequence of undirected edge. So in this case, the chain component is going to be 2, 3. All right. So you can see, right? You think of 2, 3 as one giant node, and you take the parent of the giant node, in this case 1, and the noise associated with the giant node. Okay. Again, independent noises. All right. And now within the giant node, you interpret that as a joint equilibrium distribution of some Gibbs dynamics. Yes. Yeah. Try not to think of it as a line by itself. Think of it as the class of chain, this kind of graphs, which is called chain graphs, which are graphs with like lines and arrows, right? Think of it like from graph class perspective, not like single object. Because as we will see, right, when you put them all together, like it's not independent, right? You can't like this interpretation needs some adjusting. That's kind of like a main takeaway here. Okay. All right, cool. Okay, so let's move on. All right. So as you can see, here we have previously we have multiple classes of graphs. Okay, for example, okay, so and we see that this is how the graphs are related, right? So we have this graph with undirected edges, chain graphs, okay, strictly generalizing DAGs, strictly containing DAGs. So it's a more general graph class than DAGs. And here we have ancestral graphs being a more general graph class than DAGs also. But what we see that they don't contain each other, right? In general, they don't contain each other. Okay, one example is because one has double-headed arrows, the other one does not, right? Simple way to see that. All right, so what we can do is that, okay, my supervisor, okay, and his supervisor, okay, introduce a bigger class of graphs called anterior graphs, which contains all of them, all right? And I'm gonna mention a bit what's an anterior graph. All right, so in an anterior graph, we just like a DAG. You guys are familiar with that DAGs, right? You don't have directed cycles, all right? So the analog here is that we don't have semi-directed cycles, meaning that all arrows must either point in the same way, or it's an undirected edge, right? So for example, here you have instead of 1, 2, 3, and 3 to 1, when 3 is an undirected edge. Yeah, that also counts as a cycle. It's sort of like a fake cycle. That's why semi-directed cycle, right? All right, so that's quite intuitive. All right, so that's not allowed, okay? And this is also not allowed, okay? You can't have a semi-directed path connecting bidirected edges, okay? So for example, again, semi-directed path, just like a directed path, it just means that a sequence of, it's just like a directed path where instead of every edge being directed in the same direction, you allow for some edge to be undirected. Okay. So for example, here you have 1, 2, 3, instead of 3 pointing to 4, you also allow 3 and 4 to be undirected. Okay, so that's an semi-directed path connecting endpoints of a bidirected edge 1, 4. Right? So you don't have these structures in the graph. Okay, just like a DAG, you exclude certain graphical structures, you exclude these in anterior graphs. Okay. So these sort of graphs have been studied purely from a graphical modeling perspective, okay, by my citation here. But what is the causal interpretation? What does it mean from a causal perspective? For example, DAX is SEMs and so on and so forth, the one we introduced just now, right? So what's the corresponding causal interpretation of that? All right, so this is in general a hard problem. So what I'm going to do is that I'm going to restrict myself to a subset of anterior graphs that still contains the graphs you're interested in, okay? And we will do a causal interpretation of those graphs, of this dotted circle of graphs. All right? Okay, I hope that's clear on what I'm trying to do, what my work is trying to do here. Okay. Oops. All right. So what exactly is this dotted circle? Well, this dotted circle is the anterior graphs that satisfy the chain connectedness condition. Okay. So what is a chain connected condition? Well, it means that if you recall, chain components is basically a subset of nodes in a graph such that there is a sequence of undirected edge connecting them. All right. So in this case, chain component is, just to recap, 2, 3. All right. And 1 is its own chain component. All right. So here, a chain connected just means that if it's connected, it's fully connected via bidirected edges. Okay, so for example, here you have 1 connected to 2 via bidirected edge. So it must connect to all of the chain component that 2 is in this case 3 as well, with a bidirected edge. Okay, all right, as you can see, even with this constraint, we still contains the graphs of interest, the one we talked about just now, the one with DAGs and with lines with like undirected edges and bidirected edges, right? Okay, so we still contain that despite having this extra constraint on what we are looking at. All right, so an example of a chain connected anterior graph is this over here, right? And now let's try to interpret this using our first interpretation, which we call the SEM, structural causal model interpretation, because it's you can see why as I introduce it. All right, so what we do is that first we associate to each chain component, which let me just recap, it's going to be 1, 2, 3, and 4. Okay, to each chain component, you associate a noise to it. In this case, epsilon 1, epsilon 4, and epsilon 2, 3. Okay, step 1. Step 2 is that you, based on the bidirected edges in your graph, in this case 2, 4, and 3, 4, okay, you determine the independence between the noise terms. All right, so in this case, because just like from before, because there's a bidirected edge between chain components 4 and 2, 3, epsilon 4 and epsilon 2, 3, they're allowed to be dependent. Whereas those without a chain component, we force them to be independent. Okay? Step 2. And the last step is write down the SCM, so to speak. Except now, again, just like with the chain graph case with the undirected edge, you treat that as a giant node, in this case, which I do, x23 as one giant node. And within the giant node, it's a joint equilibrium distribution of some Gibbs dynamics. Right? Okay, so that's how we get an SCM out of this, right? Cool. So that's one way of getting that's one way of interpreting this chain connected anterior graph. But what we see here is that we sort of have like imagine if you have like two chain components like that, you sort of have like a Gibbs dynamics equilibrium after a Gibbs dynamics equilibrium, right? So like an infinite time process and after another infinite time process. So the interpretation of that is quite vague, right? So what we are introducing next is a interpretation which takes into account of this, so that all the dynamics, they happen together, right? So which I think is quite aptly named the joint dynamical model interpretation, right? Everything happens jointly. All right. And I'm just going to talk about like what the main what the differences are. So let's try to interpret this graph, again, the same graph, using this as an interpretation. Okay. So using this interpretation, again, we associate to each of the chain components, in this case 1, 2, 3, and 4, with a noise. Now it's a noise process indexed by T. Okay, because it's a dynamical process, all right? So yeah, so now we introduce that index by T. And again, next step, just like from before, looking at the bidirected edges, we determine the independence between the noise process. In this case, except now, it's for all noise T1 and T2 that is indexed on, all right? So just like from before, when there's a bidirected edge between 4 and 2, 3, that is allowed to be potentially dependent, the noise process. Okay, whereas otherwise it's independent for all times T1 and T2. Okay. And lastly, you write down, instead of an SEM, you write down the joint dynamic model, right? So here, let me just break it down. What have I wrote here, right? So, okay. So here, this bit over here, the first line, this MT equals T bit, just tells you the order in which it tells you which index to pick. In this case, you pick over V. Okay, V here just means, in this case, 1, 2, 3, 4, the number of nodes, right? So here, what MT is that it sort of like cycles from 1, 2, 3, 4, and so on and so forth. You pick an order, cycle through it, and you keep the remaining nodes that is not MT the same as the previous time step. Okay? So that's the first line, that's what that says. And the second line here just says that, okay, for the MT that you pick to update, you update using this. What is this? You use the neighbor. Okay, neighbor here just means that the nodes that are connected to MT via undirected edge. For example, if MT is 3, neighbor of MT is 2, right? So you use the value of that from a previous time step, and you use the value of the parents, in this case, for example, if it's 3, it's 1, okay, of the previous time step, and you pick the current time of the noise process. Here, tau MT just means the chain component the MT is in. For example, if MT is 2, that's going to be 2, 3, so you pick from this noise process. If MT is 4, you pick from that noise process of the corresponding time, and you use that to update using this HMT function. And what is this HMT function? It's a Gibbs dynamics. It's based on Gibbs dynamics, so it's the Gibbs sampler, okay, of the chain component tau MT that we condition on the parents. And we take the equilibrium of this joint dynamical process as our joint dynamic model. All right? Cool. Okay. So what I've done, what I've talked about, what I've yapped about like so far is that how do you get from a chain-connected anterior graph G to distributions, right? The first one is using the SCM interpretation that gives you PSCM. The second one using the joint dynamic model JDM interpretation to give you PJDM. All right? So, but what good do we have if what we do is just some pretty pictures that doesn't mean anything, right? So that's where we need to show that it's valid. And it's valid if we can read off causal assumptions of the graph via Markov property. So this here represents a causal model. If we can read off causal assumptions from this causal model using our graph, then we had what we had before, right? You know, the whole fancy graphical operation kind of stuff. We can do that, right? But to do that, we need to show that's valid. Okay. So of course it's valid. Okay. So we show the Markov property of the induced distributions to the chain connecting graph. Does anyone here know what Markov property is roughly? Not in the time series sense, but more in the sense that a graph, the separations of the graph implies the conditional independence of the distribution the graph is trying to represent. So here, the independencies of your distributions that the graph is trying to represent is captured by the separations of this chain connected graph. All right, roughly speaking. Okay. All right, and this, of course, we need some conditions for this Markov property to hold. And the conditions are when the distributions satisfy. Okay, what just if you don't know what this is, just ignore that. For example, when it's Gaussians, all good. Okay, when the distributions are Gaussians, it's all good. All right. And okay, so but for the JDM one, this Markov property for PJDM and the chain connected graph G, you need some further conditions which are satisfied when, for example, when JDM is discrete, or they satisfy some sort of time continuity condition. Okay, go on. Yeah. It satisfies the conditions if it's a Gaussian. Yeah, that's it. Yeah. All right. Cool. All right. So if that's all clear, okay. So that's basically this slide. What this slide is trying to say is that under some conditions, it's valid. Okay. Our picture representation of a distribution, which in this case, these distributions using this picture is legit, quote unquote. All right. Yeah. Cool. All right. So now, because what we've done is that we represented a causal model, in this case, the SCM and JDM models that I've introduced just now, okay? So we've essentially represented those causal models using a graph. So what we can do is that, just like how we can intervene on SCMs using, how we can capture interventions on SCMs via a DAG, we can capture interventions on these causal models using a chain-connected anterior graph, purely graphically, all right? So what do I mean by that? Well, let's try to intervene this example graph here that we had from before. Okay, so just like a DAG, what you would do is that you remove edges with arrows going into 3. Okay, in this case, this and that, right? And you convert the undirected edge that 3 is connected to into an arrow pointing out of it. All right, so you convert that into that. Okay, and just like in a DAG, when you intervene on the graph, that captures the post-intervene distribution. Here, we also captures the post-intervene distribution after you intervene on node 3. Okay. All right. Cool. Okay. All right. So that's one neat thing that drops out from our interpretation. The other one here is also a single interpretation. All right. So okay, remember from before, I gave an example of a causal assumption, conditional exchangeability, right? So what that assumption is that it's an assumption between pre-intervene and post-intervene variables. So what do I mean by that? Well, the red one, X, and stuff that you don't get from observational stuff alone, right? Because here, this is a potential outcome. You don't see that, okay? So a lot of conditional causal assumptions are of this form, where it's a conditional independence between pre-intervene and post-intervene variables. So in the case of a DAG-G, we can represent these conditional independencies using what we did at the start of the talk, right? You know, the whole fancy graph magic thing, that one. We can do that for when it's a DAG. The question here is, can we do that when we have a chain-connected anterior graph instead? Okay, so the answer is yes. And here's an example of a chain-connected anterior graph. And we want to intervene on node 2. All right, essentially we want we want to do something similar on this, okay, to represent to get causal assumptions out of it. Okay, so when we intervene, let's say we want to intervene on when node 2, when X is node 2. So what we do is that first we create duplicate nodes 2, 2, and 3, 2 for the chain component that the intervene node is in this case 2. So for 2, 3, you create duplicate nodes 3, 2, and 2, 2. Step 1. Step 2, just like what I did just now, where you erase erase edges going into the node and replace it with edges pointing out. That's exactly what I do here. I erase the arrow that goes into 5 from the intervene node and replace that with a duplicate arrow that from the node I just introduced just now going into 5. Okay, so as you can see, this step and this step combined is just what I did at the start of the talk, whatever graphical magic I did at the start of the talk. All right. Okay, so there's more. Of course, there's a bit more like edges that you have to add and adjust for, but I think that's kind of not the details are not like that important for the talk. But essentially, after you do all this, you get a graph which I call phi gx, okay, that encodes the causal assumptions, aka conditional independencies between pre-intervene and post-intervene variables. All right, in this case, the pre-intervene is in red, for example, X, okay, and this is in blue. Post-intervene is in blue, for example, YX. All right, type YX. All right, okay, cool. All right. So if I've convinced you so far that okay, you can do this graphical magic on chain-connected anterior graphs. Next, I'm going to talk about the second part of the talk, constraint confounder selection, albeit a bit briefly. Okay. So recall that. Okay, why do we care about this conditional exchangeability? Well, because with this we can estimate the potential outcome, right? That's why we care about this, okay? So what we want is that what is this S, right? Because in practice, this S is not known, right? It's some sort of confounder which you have to somehow fish out from potential variables out there, okay? So one way to fish out for this set S, okay, given okay, okay. All right, so we are interested in this. We are interested in, okay, so basically what I'm trying to say is that we're interested in S that satisfies this condition, all right? So the question here says that, okay, given a graph, a chain connected interior graph G, okay, can we solve for a set S satisfying this subject to set constraints? What do I mean by that? Well, it means that the set S has to be lower bounded by set L and upper bounded by set U, lower and upper, all right? And what's the practical motivation of this set constraint? Well, the L, the lower bounded, may be something required by, I don't know, regulations or something when you want to develop a new drug, right? Something that you must include in your adjustment set S, okay? And what's U? U may be, for example, when variables outside of U are unethical to obtain. All right, say for example, like sensitive information, privacy, validations and stuff. You can't obtain data from stuff outside of U. So that's what the practical motivation of this is. So yeah, all right. Cool. Okay, so with that, we introduce a potential solution which we call constraint confounded selection, okay, which has like 3 steps, okay? So the first one, do this 5GX thing that I talked about, all right? So convert this G into a graph that represents this type of quantity and that type of quantity, the red and blue ones I mentioned just now, all right? Step 1, get that, okay? And now, once we have everything laid out on this giant graph, 5GX, it's just a separation problem, okay? And now we can use tools developed for anterior graphs to solve for this, okay? And those tools, what we can do is that we can solve this in 2 steps. The first one is do a feasibility check whether such a set S exists, okay, right? Because it can be very well that this and S satisfying these constraints don't exist, right? And then you can solve for S iteratively, node-wise, meaning that because S here, if you brute force search it, it's a set-wise operation. You have to do exponential search, right? Whereas here we can do a node-wise search, basically checking for each node and whether we're going to include that into our set S. Okay, that's the vibe, that's the flavor here of the procedure. And to allude to why I can do this, so I use these results. Okay, maximization, yeah, basically previous results being done on an anterior graph. And why can we do this? Because this here is an anterior graph. That's why we can do that. Okay. All right. Okay. So after all that talk, what am I trying to say here? All right. So TLDR. Okay. From existing graphical representations of causal models, for example, DAGs, the one with the line, the one with undirected edge chain graphs, and the one with bidirected edge ancestral graphs, we can look at a bigger graph that contains them all chain connected anterior graphs. We can generalize these causal interpretations. That's one like theoretical, like something of theoretical interest. And practically, why is this interesting? Well, because this allows for causal interpretations such as interventions and single interpretations on this class of graphs. Okay. And a potential application is that we can use tools developed for anterior graphs to solve causal problems. For example, we can select adjustment set, the one S we talked about, with constraints node-wise, which is somewhat efficient. Okay, and yeah, I think that's it. Thank you guys for bearing with me. Yeah. Any questions?